Hey guys, welcome back. We're gonna continue along in section 8.5 or with 8.5 and 8.6 today. So we're talking about solubility and solubility curves. We're gonna look at what those mean. So remember, solubility means how much of a solute can I dissolve in whatever amount of solvent that I have. So if I've got 100 milliliters of water, and remember as we go along here, a milliliter and a gram are the same thing. Okay, they're the same amount. So if I take a particular amount of solvent, the amount of solute that I can put in and get it to dissolve, that's what we're talking about solubility. Okay, now generally we talk about how much in our kind of standard is how much, if we've got 100 grams or 100 mils of water, how much can we put in at that time? So they vary. For example, sugar, you can put 204 grams of sugar or sucrose, pure sucrose, into 100 grams of water. That's double the amount. That's quite a bit. Whereas if you take, say, calcium chloride, you can only put 7.5 grams. So that's not very much. So they kind of vary. Sodium chloride, what we know is salt a lot of times as well, is 36 grams. So a lot less than that sugar as well. So what we're going to look at is a couple of terms and a graph. So what we'll see is if we've got this particular graph right here, and I've just drawn it in general. So we've got our temperature and we've got our solubility in grams per 100 grams of water. And we've got this line that's drawn here. So I'm not really worried about what the substance is. That doesn't matter at this point in time. But each substance would have their own. So a couple of terms that we'll look at. So if we say, okay, we've got, we're at 40 degrees Celsius. That's where we're going to work from here is at 40 degrees Celsius. And we say we put 100 grams of this substance into 100 grams of water. So right, that point would be right there. Okay, so we're below this curve. So we're going to say when that happens, anytime we get one that is below that line, we have what we call an unsaturated solution. Unsaturated means that you have the potential to put more solute in. Okay, so you haven't reached that limit yet per volume of water, per amount of solvent that you have in this case. So we could put more in. Okay, so we've got unsaturated, anything below the line. Now, that can change, right? Depending on the temperature sometimes, sorry, I erased a little bit there, but depending on the temperature, that can change. The same amount can sometimes be saturated, sometimes unsaturated. And we'll see that in 1 second. So if we look at another one, so if we go, let's say we put 300 grams at 30 degrees. Okay, now we're above the line. Okay, above the line means now we've got a supersaturated solution. Okay, so we're above. We have more in there. Okay, there's more there than we can dissolve for that volume of solvent. Okay, so we get above the line, we can have that as well. So we got to watch those two. Now, the key one and the one we want to know, so we're not just guessing how much we should put in, is if we said, okay, at 20 degrees Celsius, be nice if that was right on the grid, right? But let's say that's 120, 140, 160. Let's say that's about 180. 180 grams per 100 grams of water. Okay, the point where we hit the line right on the nose, that is an important point. That is called our saturation point. Okay, our saturation point, that's the point where that is the maximum amount of solute that can be dissolved in that 100, in this case, 100 grams of water in a particular volume of solvent at a particular temperature. Okay, now if I take 180 grams and I raise the temperature to 60 degrees Celsius, and I come across, and now I'm here, because I raised the temperature, my saturated solution has now become unsaturated. Okay, so if you've ever noticed, if you take hot tea or you take cold tea and you dissolve sugar in it, or hot water and cold water, that we're going to get more ability to dissolve and be more soluble in that hot water than we do in the cold water. It happens faster too. So temperature is definitely an important factor when it comes to those three terms, right? Saturated, unsaturated, supersaturated. Now, in the notes, I've included another graph or two. So one thing that's different is that if we start to talk about different ionic compounds, each one has their own. They don't all look the same. So there's a graph on there that has a whole bunch. It's got 1, 2, 3, 4, 5, 6. I think there's 7 lines on there. So you'll see that particular one, and then you have to answer questions about a particular. Which one is more soluble at this temperature, or which of these can dissolve more solute in 100 grams of water at this temperature. So you just consult the line, find the 2 points, and then figure out which one is higher. So not super difficult. Now, what does change a little bit is that with solids and temperature, we see a rise all the time. So every time we increase the temperature and we're dissolving a solid into 100 milliliters of water or 100 grams of water, we're going to see the solubility go up. The difference now is when we talk about gases, it's the opposite. As the temperature goes up, the solubility of a gas decreases. Okay, so I've included the graph for oxygen, and you'll see on that graph that it's gradually a decreasing curve as the temperature goes up. Now, the easiest way to remember this, you might think, well, why is that? If you think of this, is that means that there's more oxygen dissolved in cooler water than there is in warm water. Easy way to think of that is think of fish. Most fish live in a little bit deeper and cooler water because there's more oxygen down there. It's easier for them to breathe. They don't live near the surface. They live generally near the bottom. Some fish can live near the surface because they need a less oxygen content in the water for them in order to survive. But a lot of fish live deeper down for that reason. Another reason is that it doesn't matter what the temperature of the water is when we start. If we have some type of global event, whether it's pollution or whether it's lots of different things that could get dumped in the water, if that raises the temperature of the surface water to a higher level, think of what that's going to do. If the temperature goes up, the oxygen content goes down. So if we have thermal events that cause the temperature of lakes and rivers and oceans to go up, the oxygen content goes down, and therefore there's less oxygen for the fish to breathe with, and that can cause problems with their survival rates. And that's why we're seeing some fish go extinct, because the temperature of their habitats is going up, not enough oxygen to survive. Another factor we're going to consider in terms of solubility is pressure. So pressure is the amount of force per unit of area. And if you've taken physics, you already know this stuff, right? So force per unit of area. So that's why if you take this whiteboard and push down on your hand with it, a certain amount of pressure may hurt a little bit. But if I use that same amount of force and I put it on this marker cap, well, it hurts a lot more because I'm exerting way more pressure because my unit of area is much, much smaller. So pressure doesn't really affect solids or liquids that much. A little bit, but not much. And we're going to see this in the last unit of the year where it's gas laws, where there's a pressure law specifically. Because when we talk about gases, pressure has a really big effect, right? So the solubility of a gas in a liquid, so we've dissolved oxygen in water, let's say, it's going to go up as the pressure of the gas increases, right? So it's one of the reasons we think of, you can dissolve, like pop manufacturers, Coke, Pepsi, whatever, they dissolve more CO2 in pop than at atmospheric conditions, because they're using chilling the drink and the pressure in order to make that happen. Okay, so those are pretty straightforward, hopefully. They're all in the notes, so I don't think you'll have a huge issue with those. The other thing we're going to talk about, and makes this note a little bit longer today, is what we call concentration. And you probably know what it is, even if you don't know what it is. Right? So concentration is the amount of solute or the quantity of solute per unit volume of solution. Right? So I used to make Kool-Aid when I was a little kid, and they came in a packet. And they said, okay, put a liter of water in a pitcher. So you put a pitcher with a liter of water and then put one package of Kool-Aid per pitcher of water. So per that 1 liter. So, that tasted pretty good, but we discovered when we were little kids that if you put another package of Kool-Aid in, that was way sweeter and tasted more sugary and delicious. So we put twice as much solute in the same volume of solution. We're going to have twice the concentration. We've got way more solute, and therefore the concentration went way up. And in this particular case with Kool-Aid, so does the taste, which is kind of what you're looking for when you're a little kid. So concentration equals the amount, I'll write this down, of solute over the volume of solution. Okay, so this is what we've got. So what we're going to do with that is that we're going to take, and we're going to be a little more specific. Remember when we talk about amount, so we're going to talk about concentration equals, remember amount of solute is number of moles when we talk about amount, over V, which is volume, and it's in liters. So our units are moles per liter. Okay, that's important to recognize because when we've got a unit where it says it has to be in liters, and we don't get it in liters, that's going to mean you're going to have to do some conversion. Okay, and that's going to happen periodically as well. There's things that we call a stock solution. For example, in the back in the prep room at the school, we have those great big bottles of acid. I don't know if you've ever seen those. So we have hydrochloric acid, and it's very concentrated. What we do is we take small amounts of that, put it into a liter of water to make less concentrated acids that we deal with in class. And we call those stock solutions. So the companies that we order from, they send us a stock solution. And stock solution of hydrochloric acid, 12 moles per liter. It's super, super concentrated, right? That's stuff that if you pour that on your hand, you're going to get a terrible, terrible acid burn. It's going to eat away at your skin. So if we look at making sulfuric acid, okay? Sulfuric acid is one of the most corrosive. It's very, very dangerous. So we're going to do a quick example here that's also going to be in your notes. We've got a 25 milliliter sample of H2SO4 AQ, and then we say that it has 44 grams of just H2SO4 solid. Okay, wants to know concentration. Okay, so here's what we're asking. All right, this is from our example. Okay. So this first thing, we got to determine what we have. That's the volume of solution. Okay, that's the first thing. So I have the volume of the solution. So that's good because I want the concentration. So I have that. I have the V. 44 grams of H2SO4 solid is not what I need yet. Remember, C, I want C equals N over V. Well, I have this, but I don't have this yet. So the first thing I'm going to do is find number of moles H2SO4. So N equals 44 grams divided by, hang on here, I'm just going to cheat for a second and get my molar mass, 9808 grams per mole. And that's going to give me 0.4486. 4486 moles. Okay, so now I have what I need to plug number of moles and volume in. Or do I? So I've got milliliters, which means so far I have this 0.4486 moles. I want it moles per liter. So there's two things you can do. You can either write it in scientific notation, which you have to do at the end anyway, or you can just do the division right now. So 25 divided by 1,000, we're going to move that decimal 3 spots, right? 1, 2, 3. So that's going to be 0.025 liters. Or, if you prefer, 2.5 times 10 to the negative 2 liters. Either way, your book is going to give you that. Okay, when we do this division, we can see that we're going to get moles per liter, and it's going to come out to 18 moles per liter. So that's a super, super concentrated example. That would be a really, really corrosive acid. So we got to be really careful of that particular one. Okay, so there's another example on there as well, but you can see all I did, and I went back again, and we can't get away from it, whether we want to or not, that calculating number of moles using mass and molar mass. So the other example is also on there where you're going to see I got to convert again for these first few calculations I'm going to leave for you. Is anytime you're given a volume that's not in liters, you got to convert it to liters. First thing. So do your conversion into liters first, get that particular answer. That gives you your volume. Then normally in these, they're going to give you a mass. No problem. We've done it, hopefully 100 times you've done it now, calculating number of moles. When you have a mass, take the mass over the molar mass, get your answer, and then divide those two. So your liters got to be in moles per liter. That's the rules. It can't be in moles per milliliter. It's got to be in moles. Now, sometimes I might try and trick you and say it's in millimoles. Same thing, just do the conversion, multiply by 1,000 or divide by 1,000, depending on what they give you. Okay, so I'll leave you some of those questions from those two sections. Again, 8.5 is just kind of read through some terms that we got to know going forward. And then the quick calculation on C equals N over V that we're going to use extensively. We'll finish chapter 8 later in this week. Plan is next week, chapter 9 and beginning of 10, and then we'll finish 10 the third week. So we'll finish unit 4 the third week. And then unit 5, I'm just going to leave you guys a series of questions that you'll be able to do if you want to boost that mark up at the end. It's like an independent unit. It's on gas laws. It's basically just calculations. But again, I'll be able to answer any questions you might have going forward with those. They don't change. That's why they're laws. So they'll stay the same in the grade 12 class as well. But we got to get through chapter 10 because it continues into the grade 12. And I know most of you are planning that. Okay, so good luck with those. Again, keep sending questions. Use Lucas as a sounding board. It's fine, and it's all good, and we'll just keep answering the questions as we go. So if you do have any more, feel free to send them in. Thanks.